So periodic motion, we're going to be talking about oscillations in terms of amplitude, period, frequency, angular frequency. Technically, we should have done this chapter first before the last one we did. But we're going to be looking at simple harmonic motion using energy, and then physical situations, looking at the pendulum effect, stuff like that.
Mm-hmm.
So legs can be thought of as a pendulum. If you think about it, there's a pivot point, which is the joint hooking into the torso, and then there's a big lever that applies a force at the end of it, right? But in this case, the main part of it is that it's swinging back and forth, right?
Yeah. Yeah.
So let's look here. Here we're looking at a body attached to a spring displaced from equilibrium position is going to have something called a restoring force. What is this restoring force? Well, basically, if you compress a spring, what is the spring going to do to you?
The spring is going to bounce back at you.
Yeah, actually, I'm sorry, this is not compression.
No.
Greater than zero. So what we're doing is we're pulling the string.
We're pulling the string.
So what is the restoring force going to do?
The restoring force is going to push it back to where it originally was.
Good. So that's why the arrow in this force diagram is pointing to the left. All right. Are you with me?
I'm with you.
The acceleration will also be to the left, less than zero. Or it will be decreasing. So here we have a relaxed spring. This is the natural spring length here. So x will equal 0. There is no displacement, compression, or extension. Here we're doing the opposite. We're compressing it, and then the restoring force is going to be what?
The restoring force is going to be moving it back to the right, back to equilibrium.
Good. All right, so then these are all terms you should be very familiar with by now. We did it in another chapter, but amplitude is how high it can go from the main line, and then how low. The period is the time for one cycle. Then we've got frequency is the number of cycles per unit. Angular frequency is 2 pi times the frequency. And then the relationship between frequency and period is that they're reciprocal to each other. All right. So when we're looking at the relationship between displacement and the restoring force, you ideally will find a linear relationship in which the restoring force will be proportional to the displacement. Okay? So in other words, the greater the displacement, the larger the restoring force, but it's going to be in the negative direction. Okay? Whereas here, the larger the compression, right, the more you push the spring, the more it's going to push back. Now, the problem is that springs are made of physical materials that have physical limits on them. So the actual scenario is that you get this type of curved pattern where there is a linear relationship until the properties of the metal start to limit the amount of compression that you can have. Okay?
Yeah.
You're not the man of steel. You cannot compress the spring any further than it's going to want to get compressed, right?
Right.
But if you have superpowers, I guess you could. Here, same thing here in the positive direction. You can't elongate it. Eventually, it's no longer going to become a spring. It's going to become a metal wire, right, if you pull enough. So there has to be some sort of asymptotic divergence from the ideal case. All right. So this is an experiment people did to show the overall relationship between circular motion, rotational motion, and the periodic movement. Okay. So what they did is they took a turntable, they put a rubber ball on the turntable, super glued it there. And they put a light source down here, and when they shine the light, what happens is you create a shadow. And depending on where we are on our rotation, the shadow will shift from left to right on the wall behind it. Any questions there?
What's the purpose of this?
Just to see the relationship between the circular motion and the periodic motion. Here we have a body vibrating with an ideal spring. It's going to have the following formulas, okay? So angular velocity is k, where this is basically a constant that has to do with the stiffness of the spring. So here, this is an example that's in the book. Again, I highly recommend doing those examples, reading it. The good thing about the examples is the first part will be the setup portion. And they'll explain what you should be thinking about when you read this problem. What are the important facts, and what are the important formulas? And then there's an execute portion where they actually do the work. And then there's an evaluate portion where they're like, okay, let's see if this actually makes sense.
Right.
So if you do those problems inside the chapter and check your solution and read all that, I guarantee you it'll markedly improve your performance on these quizzes and tests. Okay.
Okay.
So here, I'm sorry. Go ahead.
We've seen that.
Yeah, we've already discussed this, but what we discussed was the Y motion, right? Motion in the Y axis. We've done the chapter after this one. Here we're looking at the X portion of that motion. So we're looking at the left and right. So this is just looking at 3 different curves in which we increase the mass on the oscillations. Okay. Here we're going to increase the spring constant, and here we increase the amplitude, how far it can get stretched. All right.
Okay.
Okay, so here we're looking at the different effects of phase angles. Where do we start out with to begin with? I think that a lot of this stuff is more just like trigonometry than application terms. Okay, so here we have the springs fully stretched out. Okay, so because it's fully stretched out, it's not moving anymore. Velocity is 0. And the acceleration is going to be pulling it back. The restoring force pulls it back this way, so the acceleration is left. Okay, and that continues. That trend continues until we get to a point where what? Where it's fully compressed.
Or fully stretched.
No, we were fully stretched.
Well, before.
Okay, so now we're going to go to a fully compressed. Then the velocity becomes 0, and then the restoring force is going to what? Push it back to the right. So now the velocities are to the right and the accelerations are to the right. Does that make sense?
That makes sense. So restoring force acts sort of like potential energy for springs.
Correct. So just like you said, we're now going to analyze energy. It's going to be transferring from kinetic while it's in between the points where there was no velocity. And then the points that are no velocity, it's fully potential. Right?
Right.
Okay. I don't think I need to go into too much detail. Just know that the sum of the kinetic plus the restoring potential of the spring, 1/2 K x squared, where x is the compression distance, is constant. 1/2 K A squared. All right?
All right.
So here we're looking at a potential energy diagram. We know that the potential energy is highest whenever we're fully compressed or fully stretched. So here we're looking at the relationship, how kinetic energy is inversely related to potential energy.
Makes sense, yeah. And there are points where potential energy is equal to kinetic energy.
Okay. So then they look at angular simple harmonic motion, flywheel, a balance wheel, sorry, which there's a spring around it. So once you apply some torque one way, all right, it'll keep going until it's fully compressed, then it'll spin back around, go that way.